Yes.
Okay, great. So let us start today. Today we will be doing. We have a long session today because we have to fill 10 hours per semester in 1 week. So we have some long sessions. So today we'll be starting the remedial session for semester 1. So you all remember what we did in semester 1: dimensional analysis, mechanics. So you should well know this, because for these reset exams, labs and there's no labs and no coursework, so your mark would be 100% off from the exam. So you need to have a good understanding of the topics that we covered. So just like the practice sessions for the 0503, which was this semester courses, we'll be doing questions again, right? So questions is the best way to go through this. So we'll go through the questions. I'll give you all questions and you all can answer them. If any problems, I will help correct. If not, we'll keep moving on, right? So I want you all to answer the questions because this is a practice for your exam, right? I don't need to answer the questions. I know the answers to the questions. So I will help you all, guide you all through, right? So the less time we spend waiting for answers, the more questions we could do in total. Right, so let's start off with dimensional analysis, right? We did dimensional analysis. Well, I didn't cover it, but one of the previous tutors covered it with you all for the first session. So let's start with dimensional analysis. What are some applications of dimensional analysis? When can we use dimensional analysis?
First, to convert units and to verify that the units are correct.
Right, so we could use it to determine if an equation is correct. So like for example, if we have force is equal to momentum times velocity, by looking at the dimensions of the left side and the right side of that equation, we would realize that they don't match. So that way we would know that that equation is not correct, right? So we could use it for that. I'm seeing an answer in the chat here to derive new equations. So that is also correct, but correct to a certain point, right? So we could use it to get new equations, but we cannot verify the equations. So that is actually a limitation of dimensional analysis, right? So, well, I just mentioned the limitation. One of the limitations of dimensional analysis is it does not give equations that contain constants with no unit, right? So for example, in the equation for kinetic energy, we did this multiple times over all the semesters, right? Kinetic energy is equal to a half mv squared. Now dimensional analysis could show that the units for energy is equal to the units for mass multiplied by velocity squared, but the dimensional analysis cannot give us that half in that equation, right? So that is like a limit of dimensional analysis. Right. So So give a little more explanation of that. It does not account for the difference between properties with the same elements.
So like if two, I don't know what the word is for it, but like if for example, just hypothetically, if like area and volume had the same, if they were both used meters twice, it can't tell the difference between them if you use dimensional analysis. It can't tell if it's referring to one or the other.
Okay, yes.
Yes.
So, like, for example, a better example would be like kinetic energy and
I think
potential
so.
energy.
I'm some.
Sorry?
I think there was an example in the note that had, I think, torque or moments or something like that. That I can't differentiate between them, but I don't remember exactly.
It probably is torque and moments because they have the same units, and we could also look, like, for example, at kinetic energy and potential energy, right? So they both have the same units, but looking at the units, we cannot differentiate if the energy is kinetic energy or potential energy. Same thing with as you said, torque and moments, right? Both are forced by distance, but one is multiplied by a perpendicular distance and one is a distance along the axis, right? So that is another limitation of dimensional analysis. So now for the second question, I want you all to determine what are the dimensions of kinetic energy and potential energy, right? Well, as I just mentioned, both of them are the same. So how would we determine what is the dimensions of energy, kinetic energy? You could type it in the chat. That shouldn't be hard to type.
It will be, mass would be capital M. Velocity is length over time, so that is capital L, capital T to the minus 1. And then you square it or something like that. I don't remember the last part, but I remember.
Squared, yes.
But all I remember is that it had to be capital M, capital L, T to the minus 1. And then it would be like ML for the ending would be ML squared T to the minus 2.
Right, yes, so that is correct, but let me actually write it out because I realize this might be a little. Alright, someone wrote it out here, right? But I just realized with the subscripts and stuff, it would be a little hard to read.
Sir, the little the hop thing that was to put to the power of.
Yeah, I know, but yeah, so it is correct what you wrote. I'll just write it out still. So in the meantime, I'm going to just connect this iPad. So in the meantime, I've given you another question here, right? So you all could do this, and then after we will come back to that one. I'll write it out. Right, so I sent two vectors here, right? So after dimensional analysis, we went into vectors and scalars, right? So I am sending two vectors here on the question. I want you all to sketch the vectors on the Cartesian plane, right? So basically, you're sketching them as if you're drawing a simple graph, x and y, right? And I want you to determine the magnitude of each one of them. So the magnitude of P, the magnitude of Q, and to determine the angle between both of them. Right, so let me just type that, sketch magnitude and angle. Right. Right, you all finished?
Yes, sir.
Alright, tell me when you all finished and I'll go back to that one, the dimensions one. Alright, so I've seen some answers in the chat. We'll go through it now and we'll check and see. We'll double check that, right? Okay, so let's continue. Right. So we talked about dimensional analysis. We talked about vectors and scalars. Now we found the magnitude, the angles, we sketched the vectors, but actually we didn't do addition and subtraction of vectors, right? But as we know, this is easy, right? Because let's take our example here. If we have to have P plus Q, I'll just draw it, write it next here. This now is just equal to the I components added to each other plus the j components added to each other, right? So it would be 4 plus 6i plus 5 plus 0 j. So this would just be equal to 10i plus 5j, right? So we didn't do the addition there but previously, but any vectors, when you add them, you add each component to each other. So you don't add a I component to a j component, you just add the I components together and the j components together. Now we did not do dot products and cross products, which would be multiplication of vectors, so I wouldn't go through that. Right. We also saw accuracy and precision and talked about the difference between them. Now in classes we also talked about random error and systematic error. So what is the difference between what is random error and what is systematic error?
So random errors happen by chance, like they make your readings scatter like all over the place. And systematic error is when something happens because it's consistently wrong.
Right. So random error are errors that cause scattering of the results, right? So it could be higher sometimes, higher than the true value or lower than the true value. But systematic errors, it consistently makes all the readings either greater than the true value or smaller than the true value. So to minimize random error, how can we minimize random error?
By taking multiple readings.
Right, taking multiple readings and taking an average. But that would not work for systematic error, because in the systematic error, all of the readings are greater or all of the readings are smaller than the accepted value. So all of the readings would be taking the average, we would still have a value that's either greater than the true value or smaller than the true value. So to eliminate systematic errors, we actually have some examples of random error. One example of random error. So exactly when the pendulum is at gross error. I'm not too sure what you mean by gross error.
Everything correctly on the wrong or the wrong value, or would that still be under random?
That would still be random error because
Okay.
sometimes you might time it to be faster than the actual oscillation. Sometimes you might time it to be longer. Writing down the wrong value should not happen. But if it does happen, sometimes you might write a bigger one, sometimes a smaller one. But that should not be an error in general. But yeah, those are examples of random errors. Now, errors. As I see in the chat here, example a broken ruler. So if 1 millimeter of the ruler is broken, all your values would be measured to be 1 millimeter shorter if you use that end of the meter rule, right? So in that case, that systematic error is also a zero error, where the zero on the scale is not actual zero, right? So yes, those are some examples of random and systematic errors. Some errors, they also cause the position of insurance, as we saw, okay, the measurements over right? That is like an example of right. So let us move on now to some mechanics. So we saw before the mechanism, what's the what's the equation? Right, velocity divided by time, right? So acceleration, we saw we could write the change in velocity over the change in time, right? Now right, so we had some graphs. We saw displacement time graphs and we saw velocity time graphs, right? Now if we have a displacement time graph, let's say that was our graph, right? Okay, I'm going to draw some examples. So in this displacement time graph here, how can we write this displacement time graph? If this is the displacement time graph of an object, how do you describe the motion of this ball? Right, as seen in the chart, acceleration is the rate of change of velocity with respect to time. Yes, so that is a correct definition. Right. With this displacement time graph, how do you describe the motion of this ball in words? Nobody?
So would it be that the object is stationary?
Right, so it is a stationary object, right? Because the displacement is not changing with respect to time. So if displacement is not changing, the position of the ball in this case is not changing, therefore it is stationary. So how about this graph? How do we describe this graph? That's a straight line, right?
They have a positive slope and the otherwise increasing as time increases.
It has a positive slope. The displacement increases with time. So what would be the gradient of this graph?
One?
Sorry?
Oh, it's positive.
Sorry, just repeat that. You broke up just now.
I was asking if it would be positive. Oh,
What is the what is the gradient of a displacement time graph equal? Gradient is a constant value, right? So constant velocity. Now, how about this graph? How would we describe this graph? what would we say is happening to the ball in this graph? Right, so the object is accelerating in this case because with as time increases the curve gets steeper, right? And as we know, the steepness of the curve represents the velocity. So the steeper the curve, the higher the velocity. So the velocity is increasing with time, therefore the ball is accelerating. Now if I draw the graph like this, how would we describe this one? These are things you should be able to watch and recognize, because in the exam we have 3 hours to do 5 questions, so can't spend too much time thinking about this. Nobody?
So does it start at it starts at a high acceleration and decreases to 0 as it bends?
So actually not in this graph. So in this graph we see that at 0 time it has a far displacement, but the displacement decreases with time, right? So the graph starts going downwards. So if the displacement decreases with time, the object is moving towards the starting point, right? Because the starting point or the original position, what we call zero displacement, which would be the origin. So the object is moving back towards the zero displacement. But if we look at the slope of the graph now, we can see that it starts off with a very small slope, and then afterwards the slope increases with time. So as we know, the slope of a displacement time graph is velocity. So originally the object was moving with a small velocity, and then the velocity started increasing with time. Therefore, the object is actually accelerating. It's just now that it's accelerating back towards zero displacement, right? So both this and the previous diagram are examples of accelerating. The difference is that it is accelerating in different directions.
Very good. What other one was that, please?
Right. So in this, let me draw it out, right? So let's say this is the original position, right? We could call this O, and the ball moved across here. So this, we'll call this position P, right? So in this graph here now, O would be at this point and P would be over here. So now the ball is moving from P towards O, as we see in the graph. As the ball goes from zero time, as time increases, the line goes from P towards O. So the ball is moving in this direction, right? Now, originally, the slope of this graph is almost zero, right? It was started off horizontally, and then afterwards, it started curving downwards, right? So originally, the velocity was almost zero. As we saw, a stationary object, we could draw the graph like this, right? A flat horizontal line for a stationary object. So originally, the ball was stationary, and then it started moving with a very small velocity, and as we could see, as time increases, the slope increases, right? And as time increases, it gets even more and more steep. So therefore, we know that the slope of the displacement time graph is equal to the velocity. So therefore, we had a small velocity at this point, and then as time increases, the velocity keeps increasing. So we know when velocity increases, that is an acceleration. So this graph shows acceleration. The difference between this graph and this graph, so both of them show acceleration. It's just the second graph shows acceleration from O towards P. The first graph shows the acceleration from P towards O. So if this is O and P and P and O, right? So both of them show acceleration, just in different directions. Is it better now, or you still want some more clarification?
That's good, thanks.
Okay, so let me give two more examples for this. Let me just go further down and draw. Right. So how would we describe this graph? This is displacement and this is time. How would you describe this?
So it has a steep rise. It starts to flatten out as it increases. So that indicates that it's no longer accelerating steeply. Basically it accelerates and becomes somewhat stationary.
Right, so it started off with a steep slope, which means it started off with a high velocity, but then after some time the slope gets less and less steep, and so the velocity gets smaller and smaller. So the velocity started off high and it decreased, so the velocity was decreasing and then it went as low velocity. So we could say that it is decelerating, right? The acceleration is the velocity is being reduced, so it is decelerating. Now, how would we describe this? Right, so the velocity is decreasing as well. So it started off with a very steep slope, and then afterwards the slope gets less gradual, so the velocity is decreasing and this object is decelerating. Right, so these are displacement time graphs. Now we saw these graphs called velocity time graph. Velocity time graphs now, right? So in these velocity time graph, this should be a straight line parallel to the time axis, right? How would we describe the motion of this body, this object? It's not accelerating, right? Because we know that the gradient of a velocity time graph is equal to the acceleration. Now in this case, this is a flat line, so the gradient is equal to 0. Therefore, the acceleration is equal to 0. So this graph shows a body that is not accelerating. Now, how do we determine how far has the object moved? In this graph, is the object moving and how far has it moved? How do we determine how far it moved? Right, the area under the graph gives the displacement, right? So this is how far this object moved. So if we determine the area under this, so the velocity, this this is a rectangle, so you could just multiply the length by the width, and we could determine the area under this graph, and then we would know how far the object moved. Now, so this graph basically it represents a constant velocity graph, a object moving with constant velocity. Now, what does this graph represent? Right, so this is a graph with constant acceleration, right? It's a straight line graph, and the acceleration is the gradient, so this is constant acceleration. Right, so let's take a small example now. If we have a velocity time graph right, so this is a velocity time graph, velocity in meters per second, time in seconds. So determine the distance, displacement after 5 seconds determine the acceleration at 11 seconds yeah, so determine these two things. And the velocity at 7 seconds. You could type it in chat when you finish, or you could just unmute and say. Right, so in the first part, we need to determine this area here, right? So that is a triangle of base 5 and height 2. So the area is just equal to the base by height divided by 2, which is 5 multiplied by 2 over 2. So we get 5, and unit is meters, right? So let me write it with the units. Equals 5 seconds times 2 meters per second, so the seconds cancel, divided by 2. 2 cancels, so we get equal 5 meters. In the part 2 now, we need to determine the acceleration at 11 seconds. So the acceleration at this point here. So to determine the acceleration at that point, we need to determine the gradient at that point, right? So the gradient is the change in y divided by the change in x. Now we see between 10 and 12 seconds, it's a straight line. So we could use those points because we know the y values at 10 and 12 seconds and we know the x values. So we could have the acceleration is equal to the change in y, which would be equal to 2 minus 0 over the change in x. This would be equal to 10 minus 12. So this would be equal to 2 over negative 2, which should be equal to negative 1 meters per second squared, right? So we could write it with the units. This is velocity, and this is seconds. So this is how we get meters per second squared. Right. So that is part 2. And part 3 now, the velocity at 7 seconds. So 7 seconds is approximately here, right? 7. So but just by looking at the graph, we see that at this point there is a constant velocity of 2 meters per second. So part 3, the velocity at 2 meters per the velocity at 7 seconds would be 2 meters per second. Right, any questions about that? If not, let us move on. So we saw there were equations of motion. There were 3 equations of motion, right? Some people, as I mentioned, call it the Suvat equations. Some people just mention them to be equations of motion. So what are these 3 equations of motion? Some people say SUVAT because it contains these terms, right? SU, that should be a UVAT, right? So what are the three equations of motion that use these terms? Right, V is equal to U plus AT. V squared equal U squared plus 2AS, and there was one more.
S equals UT plus half AT squared.
Right. So we should be able to use these equations, right? So let's take an example of a ball falling. Right, the ball is falling from right. A ball is thrown downwards off the top of a building of 100 meters. Right, 100 meters too big. 20 meters with a speed of 3 meters per second. So I want you all to determine the velocity after 5 seconds. Right, I'll give you that G is equal to 10 meters per second squared. Right, just for this example, we'll leave it as 10 meters per second squared, just for simplification. So I'm changing this question, right? I'm changing it to 0.5 seconds. You could type it in the chat or unmute and say when you're finished. Okay, so let's start. Right. The question didn't ask for direction, so in this case you don't need to specify the direction. Right, so after 0.5 seconds, we could use the first equation for this, right? So for part I, we have v is equal to u, which we know is 3, plus a times t. Now, the acceleration we were given to be 10, and the time is 0.5, right? So this is equal to 3 plus 5, which is 8 meters per second. For these, I'm going to write everything with the units just to make everything clear, right? So 3 meters per second multiplied by, plus 10 meters per second squared multiplied by 0.5 seconds, right? So the seconds cancels with the 2 here, so we get minus 1, right? So this would be 3 meters per second plus 5 meters per second, which is 8 meters per second. In part 2, determine the velocity when it hits the ground. So in this one, we have to use the second equation, right? Because we need the distance. We don't know, at least before doing part 3, we don't know the time when it hits the ground. And we don't know, well, we want to find the velocity when it hits the ground. So we can't use the first equation because we don't know the time when it hits the ground. Same thing with the third equation. We don't know the time when it hits the ground, so we can't use the third equation. So we have to use the second one. So we have v squared is u squared plus 2as. So we could write v is equal to the square root of u squared plus 2as, which is equal to the square root of u we were told was 3 plus 2 times 10 times 20. So this is the square root of 3 plus 20 by 20, which is 400. Is equal to the square root of 403, which is equal to 20.2 meters per second.
Excuse me, sir.
Yeah.
Don't we have to square the 3?
Oh, sorry, right. 3 squared, so this would be 9. So this would be square root of 409, right, which is 20.22 meters per second. Right. And for part 3, we need to determine the time when it hits the ground. So what we could do, knowing our answer for part 2, we could substitute v into the first equation and determine the time. But if we did make any mistake in our calculation in part 2, we would get the answer wrong for part 3 as well. So to calculate part 3, the safest thing to do would be to use this third equation here. Well, we could use the third equation, but it actually is simpler to use the first one. So let's just use the first equation. So we can use back v is equal to u plus at, and we need to calculate t, right? So v minus u over a is equal to t. So this would be 20.2 minus 8 over 10. So this is 12.22 over 10 so this would be equal to 1.22 meters per second. 1.22 seconds. Right, so this is actually simpler than using the third equation. Right, any questions? Okay, now these equations, I just this question is a question where the ball was dropped vertically downward, right? So this is in one direction. Now we also covered two-dimensional motion, right? So motion in the x-axis and y-axis. So for example, projectile motion. If I threw the ball, if someone throws a ball upwards at an angle, it would go upwards, but it would start falling down. Now in this question, there's motion upwards and there's horizontal motion as well, right? So this is an example of 2D motion, right? And what we saw is that we can separate these components and use these equations of motion separately, right? So we can find the equations of motion for upward motion only, and we could use the equations of motion for horizontal motion only. Right? So to do that, we had to separate the components into the components of the velocity into the x component and to the y component, right? So we did a question like this, well, we did vectors questions a little bit earlier. And this not really separating components, but finding the angle between them. So if the initial velocity at this point here is v, right? The x component, how do we determine the x component of this velocity? Let's say the magnitude is equal to just v, right? How do we determine the x component of this velocity? Recall we could have drawn this triangle with this angle here. This is Vx and this is Vy, if this is V. So knowing this, how do we determine the x component of the velocity? Well, you would need to know dimensional analysis. I'm not sure what you mean by advanced dimension, like pendulum or period. I'm not too sure exactly.
Like to show the relationship between it. I don't think it came last time, but it's in these tutorials. Or is it just like using dimensional analysis to show if they're the same?
So you will need to know dimensional analysis to show like the homogeneity of an equation, or to be able to say that an equation is not homogeneous. So an equation,
is that it?
Yes, I believe that is all. So we wouldn't be going into like determining the power of the like for example the power of time or the power of distance to actually calculate that to make the equation. I think in one of the coursework last semester not last semester, in semester 1 in the coursework I had tested that, but I wouldn't be testing that now. But you need to know the homogeneity of the equation. Okay, no problem. Right. So how do we determine the x component of this velocity? the x component and the y component.
So do you just want the formula
Yeah,
or
just the formula, yeah.
for the x, in this case the things sine theta, and for the y the symbol cos theta.
Right, because remember, cos theta is equal to adjacent over hypotenuse, right? So that would be Vy over V, and sine theta is opposite over hypotenuse, which is Vx over V. Right, and when you rearrange, you could get this. So by separating this velocity into the horizontal and vertical components, we can apply the equations of motion to the vertical direction and the horizontal direction. Now, in projectile motion, what we need to remember is that in the vertical direction, there is always the acceleration due to gravity, and that points downwards. Whereas in the horizontal direction, if we assume that air resistance is negligible, which in all the cases for this course we will be assuming, in the horizontal direction there is no acceleration to the projectile, right? So our equations for motion in the x direction, a would be equal to 0. So ax is equal to 0, and we write ay is equal to g. Right? So this is basically what we need to know, and then we are applying these same three equations which we saw earlier to determine whatever the question asks for. Right? So we can take a little break now, and we'll start back at 3:20.
So you could scroll to the diagram that it drew, please.
Okay, so let's move on now. We did some motion, now let's go into some dynamics. Right, so when we are dealing with dynamics, we saw Newton's laws of motion, right? So we saw Newton had 3 laws of motion. Now what are the 3 laws of motion? Newton's 3 laws of motion. Let's start with the first one. Newton's first law of motion.
Our body will continue in its state of rest or uniform motion in a straight line unless acted upon by an external force.
Right. Yeah, so basically our body will continue in a state of rest or uniform straight line motion unless acted upon by an external force. So what's Newton's second law? Newton's second law.
The net force acting on a body is directly proportional to the rate of change of momentum of a body in the same direction of the change in momentum.
Right. So basically, Newton's second law is kind of like, we could think of it as a definition of force. The force acting on a body is directly proportional to the rate of change of momentum of the body, right? So we could write this for a body that is not changing mass. We could write this as F is equal to ma, right? So this is where we get that formula from. Now, what is Newton's third law? Right, so we could state it a little more formally as if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. Right? So those are Newton's 3 laws of motion. Right? Now, Newton's second law of motion deals with talks about the rate of change of momentum, right? So what is momentum? Right. Momentum of an object is equal to its mass times its velocity. So we saw a law of conservation of momentum, right? So the law of conservation of momentum is if no external forces are acting on the system of bodies, then the total momentum in a given direction is constant. So the momentum before the collision is equal to the momentum after the collision if no external force is acting on that collision, right? So talking about collisions, before we do some question on collisions, right? We saw there are different types of collisions, right? There's elastic collision and inelastic collisions, right? So what is an elastic collision?
Elastic collision is where there is no loss of kinetic energy, and inelastic is where there is a loss of kinetic energy.
Right. And what about momentum? Does momentum, what happens to the momentum in an elastic collision and what happens in an inelastic collision?
Oh, it is conserved in elastic and it is lost in inelastic.
So actually momentum is conserved in both elastic and inelastic collisions, but in elastic collisions kinetic energy is conserved, but in inelastic collisions kinetic energy is not conserved. And we saw, so elastic collisions, example could be like pool balls, right? Those are very similar to elastic collisions. We saw another type of collision, which, well, not really a separate type of collision, but a type of inelastic collision, which is called totally inelastic collision, right? So what occurs in a totally inelastic collision? there's one thing special about a totally inelastic collision, which is what occurred.
Sorry, answer the chat.
Oh, sorry. Right, in a totally inelastic collision, momentum is conserved, kinetic energy is not conserved, and the objects stick together, right? So basically, there is some sort of deformation, permanent deformation of the objects in a totally inelastic collision. So, like in an inelastic collision, when we see the two pool balls hitting each other, there's no deformation of the object, right? The balls remain in their circular shape and they knock each other away for elastic collisions. But for totally inelastic collisions, the objects stick together. So for example, in a car crash, when two cars hit each other moving in the opposite direction, the cars crash and they stick to each other. So there is a permanent deformation of the body in inelastic collisions, right? In totally inelastic collisions, they stick together. In regular inelastic collisions, they still have some sort of deformation, right? So let's do a short question on collisions, right? If we have a ball moving at (10 meters per second in this direction and another ball, this ball has a mass of 2 kilograms. This ball has a mass of 5 kilograms, moving in this direction with a speed of v, right? And we want to determine, so this is before the collision. After the collision now, the first ball or let's say after the collision, both of them meet and they stick together. Both of them, they deform and they become one big ball and they have 0 velocity, so 0 meters per second. So this now is a cello kilogram ball, right? This is after the collision. So we want to determine what is the initial velocity of the ball on the right side, the 5 kilogram ball. So we need to calculate V. Right. So the momentum before the collision is equal to the momentum after the collision by the law of conservation of momentum. Right. So the momentum before the collision is 2 kilograms multiplied by 10 meters per second minus v times 5 kilograms. Right? The negative is here because this is moving in the opposite direction. So this is before the collision, the total momentum, and now this is equal to the momentum after the collision. Now after the collision there is no motion, right? So the two balls merge and become one ball, and there is no motion. So the momentum after the collision is equal to 0. Right? So now we could just rearrange this. So this is 20 kilogram meter per second is equal to v times 5 kilograms. Therefore, we have, we're not writing this as a minus yet. We're leaving this as positive, right? We would see when we are doing the question that we would get a negative v. So this v, we leave it as positive. So this would be negative v times 5 kilograms. So therefore v is equal to 20 kilogram meter per second over negative 5 kilograms. So this cancels and we would get negative 4 meters per second. Right? So what we notice here is that this velocity is negative, and the reason it is negative is because the ball, the 5 kilogram ball, was initially moving in the opposite direction. Right? So that is why we get a negative answer for v. Right. We also saw impulse, right? Impulse, the definition of impulse was just the change of momentum, right? So impulse we saw was used to study the impact force during collisions. So in sports, for example, we want to reduce the amount of force on our bodies, right? So we would have more energy to carry on playing the sport, and we could use that extra force for other times during the sport, and also we would reduce the amount of damage and repair time needed in our bodies, right? So for example, when we are jumping, we bend our knees before impact, right? Because when we bend our knees, we reduce the time it takes to make a full stop, go from the velocity we jumped from to complete stop, and increasing the time it takes to make that full stop, it reduces the amount of force on our knees, because we know from Newton's second law, F is equal to the change in momentum with respect to time. So if delta t increases, the force is smaller. So the force on our knees is smaller when we bend our knees upon jumping, after coming back to the ground when jumping. Or for example, a cricketer catching a ball, when he catches the ball, he doesn't leave his arms right there. He pulls back his arms to increase the amount of time it takes for the ball to make a complete stop. So the force on his hands is not as great. So he does not feel as much pain in that case. Right? Now we also saw the moment of a force, right? So what is the moment of a force? What is the moment of a force? Right, so we could write the moment of a force as the force times the distance, right? So the definition is the moment of a force is the product of the force multiplied by the perpendicular distance from the line of action of the force to the pivot, right? So we have to distinguish this from torque, right? So the moment is the force multiplied by the perpendicular distance from the line of action to the force to the pivot. So let's take, for example, you had a lab, right, with a ruler balancing on a retort stand. So on this side there were weights, and on this side it was the weight of the ruler from the center of the mass acting downwards. So the moment on the right side was due to the weight, right? So the distance is this distance, the moment on the right side of the pivot, which is perpendicular to the direction of the weight, right? So, and this is along the line of action of the force to the pivot. Basically, this distance is along the ruler. So in this case, we know the moment M is equal to the force, which is the weight in this case, times this distance here, right, times d. We know that is equal to the moment. Now there was something called the principle of moment, right? So what does the principle of moment state? Right. In the exam you would have to give a little more explanation, but at least for here I'll accept these, right? So the sum of the clockwise moments is equal to the sum of the anti-clockwise moments, right, for a body in equilibrium, right? So you need to state that as well. You need to make sure you state for a body in equilibrium, right? Right, so that is the principle of moments. So let's utilize the principle of moments for the same. You did it in the lab already, but let us just do it back here. So let's say we had a force of 10, we're using 10 too much, 20 newtons acting at a distance of 30 centimeters from this pivot. And here we have a force acting downwards, and this is acting at 50 centimeters from the pivot. And we want to know what force would balance this system. What force F would cause this system to be in equilibrium? So we need to determine F, the value of F that would cause this system to be in equilibrium. Right, so for the principle of moments, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments, right? So the clockwise moments is the moment due to the 20 Newton force. So we'd have 20 times 0.3, right? Because we need to convert this from centimeters to meters, is equal to F times 0.5. Therefore F is equal to 20 times 0.3 is equal to 6 divided by 0.5, which is equal to 12 newtons. Right. Now if we had to determine the mass needed to be hung there, so the mass would just be equal to the force divided by G. If we use G as 10, we could use this as 1.2 kilograms, right? If we needed to hang a mass to create this force F, right? So just remember this too, that for moments, when you're calculating moments, it's the force by the distance, right? Not the mass times the distance. So like if here, instead of having 20 newtons, I put 2 kilograms, you would need to convert this 2 kilograms into 20 newtons and then do the equation, right? Sorry, and then use the principle of moments, right? So you need to look at your units and make sure the units are in what is needed for the equation. Right. So now if this force F, we moved it closer to the pivot. So if we moved F to this point here now, will that increase the moment or decrease the moment? Due to F. If F is now moved to this location, no, so actually in this case the moment due to F would decrease if it moves closer to the pivot, because when it moves closer to the pivot, the D in this formula here, this D decreases, right? Therefore the moment would decrease if the force is moved closer to the pivot. If it's moved further away from the pivot, then the moment would increase, right? So it's kind of like if you are using a scissors to cut some paper, right, or cut something thick. When you hold the scissors close to the pivot, you have to apply a stronger force to the scissors to allow it to cut the paper. Say you have to cut 3 or 4 sheets of paper and you're holding it closer to the pivot, you have to apply a greater force. If you are holding the scissors further away from the pivot, so at the end of the handle of the scissors, you apply less force to make the cut, right? That's just like one example. Right. So let's move on to forces now, right? So let's say we have a box on an inclined plane. The incline is at 60 degrees and the box has a weight of how much? Let's say 50 newtons, right? It has a weight of 50 newtons. Right? Now we have to let us try to draw the forces on this box, acting on the box, that is parallel to the plane and perpendicular to the plane, and also draw the direction of the weight acting on the box, right? So I'll give you all a minute to draw it yourselves and then I'll do it. Right, so the weight now acts from the center of mass, acts vertically downwards, right? So this is the weight, this is equal to 50 Newton downwards, right? Now there is the normal force acting on this box, right? Remember, the normal force acts perpendicular to the surface of contact between the two objects, right? So the normal force is the force that pushes upwards from the table. So that normal force acts in this direction like this. Now there is also the force acting in this direction. That force is due to the weight. This is the component of the weight that is acting in a direction that is parallel to the direction of the plane, right? So we could separate this force. We can separate the components of the force like this. Now, if we have to determine the magnitude of these forces, how do we determine this? So this, we can draw this we can separate this into a triangle like this, right? Where this is equal to the weight, the hypotenuse is equal to the weight, this angle is equal to theta, which in this case is 60 degrees. So I'll just write the numbers one time. So this is 50 newtons, this is 60 degrees, the opposite is equal to the so let's throw it back here. Normal acts and right, so this is a right angle here, which is this right angle. This angle here is equal to 60 degrees. So we have here, this is F, and here we have the normal force. Right? Sorry, I made an omission. Right? I omitted two forces. Oh, let me do this. I made an omission which was the component of the weight in this direction and the frictional force which acts in this direction. Right? So this is the frictional force would be acting to keep the object in its original position. Right? And F was the component of the weight that causes it to slide down the slope. Now, if we had only drawn N in that direction, then the object would have just moved upwards, right? So the component of the force that is perpendicular to the slope cancels out the normal force. So there is no motion that is perpendicular to the direction of the plane. So now, if we have to determine the component of the weight that is perpendicular to the plane, that would be this component here, right? We could write that as W in the y direction. That is the weight component of the weight perpendicular to the plane. And F would be the component of the weight that is parallel to the plane, right? This would be the frictional force. I'll write that as FF, right? I could actually write F in this case as WX, just to simplify. So if we have to determine the component of the weight that is perpendicular to the plane, that is WY, we use this triangle here, right? So we draw a triangle like this, where there is a right angle here. Now we would know that this angle here is equal to 60 degrees. Right, we could see that because here is 90 degrees as well. Here we have a 30-degree angle, and so therefore this would have to be 60 degrees, which is equal to the angle of the slope. So we could draw this triangle. We can draw that back here, where we have 60 degrees. We have WY on this side. Here we have W, on this side we have WX. So the Y component, which is the component that is perpendicular to the direction of the plane, we can write this as WY is equal to W times cosine theta, right? And we could substitute this. This would be equal to 50 times cosine of 60. I believe this would be equal to 25. You just want to verify that for me. And Wx would be equal to W times sine theta, which would be W times sine of 60. Sorry, this would be 50 times sine 60. And this would be right. So yes, in if you have to find the magnitude of Wy in this case, the magnitude of Wy is equal to the magnitude of the normal force, and the magnitude of Wx would be equal to the magnitude of the static frictional force, right? Now the directions would be different, right? So Wy is in the opposite direction to the normal force, just by definition, right? The normal force is in opposite direction to the weight. The frictional force is in the opposite direction to Wx, again just by definition, because the frictional force acts in a direction to oppose any type of motion, right? But the magnitudes will be the same. So this would be equal to 25 newtons, and this would be equal to 43.3 newtons. Right. Do you all have any questions about this? I know I made a little mistake at the start, so I'm not sure if I fully was clear. Okay. Well, if there are no questions, then let us move on. Right, so we talked about frictional forces just now. Well, static frictional force, right? So there's two types of friction, static friction and kinetic friction, right? So what is the difference between static friction and kinetic friction? And which one is greater? No, I didn't give any coefficients. I just asking in general. What is the difference between static friction and kinetic friction, and which one is greater? Right, so static friction is the frictional force that prevents motion, right? So there is no motion of the object when static friction is being applied. But for kinetic friction is the force that resists the motion of the object. So the object is moving, but there's a force that opposes that motion, so that is the kinetic frictional force. So the static frictional force is larger. Right, so that is correct. There was also one more force we saw, which was tension, right? So tension is like, for example, pulling a box through a rope or a string, right? So tension is the force that is directed along the length of that string, and it pulls equally on both sides of the string, right? Now let us do one more. Well, actually, right, so we talked about elasticity as well, right? So elasticity, for example, in springs, or for example in springs, is the property of the spring which causes it to be restored to its original shape after being stretched, right? And we saw Hooke's law, right? What does Hooke's law state? Right, the force needed to extend or compress a spring by some distance is proportional to the distance. Right, we can write it in the form F is equal to Kx, where K is the spring constant. Right, so for objects that are more elastic, they have a larger spring constant, right? And we saw a point in the a point called the limit of proportionality, right? So what is the limit of proportionality with regards to Hooke's law? We also know it as the elastic limit. Right, so the limit of proportionality is the final point where Hooke's law applies, right? And at that point, the spring or whatever object it is becomes permanently deformed if any more force is applied, right? So when this occurs and there is permanent deformation, this is called plastic behavior, right? But the point until the limit of proportionality, where it still obeys Hooke's law, that is called elastic behavior. And when it does not obey Hooke's law, that is called plastic behavior. Right? So in this graph here, this is force versus extension. at this point here, it is no longer linear, right? So at this point, this is the limit of proportionality, right? And the points up till there, so the red part of this graph, this is a straight line, right? So we call this the elastic region, and the blue part of this graph, it no longer is a straight line, right? So we call this the plastic region. Now, if we have another object that has a graph like this, let me change the color. Which material is the stiffer material, or which material has the higher spring constant, the larger spring constant? The one that is red or the green one?
Green.
Right, the green one has the larger spring constant, right? So we can determine the spring constant by the gradient of this graph, right? Now, right, so let's take a simple question, right? So we have a spring at equilibrium at equilibrium, the length of the spring is 10 centimeters. Now, if it has a spring constant of 5 kilograms per second, determine the force needed to cause an extension of 2 centimeters. Right, so we want to extend it by 2 more centimeters. So determine the force needed to extend the spring by 2 centimeters if it has a spring constant of 5 kilograms per second squared. You could say it or you could type it in the chat when you're ready. So we have the equation F is equal to Kx, right? We know what the value of K is. The value of K is 5 kilograms per second square, or this should be sorry, electricity just cut off by me, right? You seeing me now? Is it connected again? Well, you seeing the screen or hearing me? Hello? You could message or unmute if you are hearing.
So I can hear you, but
Okay.
the screen a little blurry.
Okay. It might come back better when the internet restore, because I switched the data right now. So, alright, well, I might have to finish after this question then if it does not get back clear. But basically we have the formula F is equal to K times X, so we'd have 5 kilogram per second squared for the value of K, and the extension is 2 centimeters, but we need to convert this to meters, right? So this would actually be multiplied by 0.02 when we convert this to meters. So what we would get is 5 times 0.02, which is 0.1, and the unit of force is newtons, so we get 0.1 newtons for this question. Right. Are you seeing my screen blurry still, or is it clear now?
Yes, sir.
Yes as in blurry or clear?
Blurry.
Alright. It might take a while for my internet to come back. So let's do one more theory question for today, and then we'll end it for today, because I don't know how long before the internet is back up. So what is the difference between laminar flow and turbulent flow? And draw this in, you can draw this, draw it out. So draw the, state the difference between laminar and turbulent flow, and I also want you to have it in diagram form. And well, actually, if it's blurry, I wouldn't be able to draw it good. So let's just state the difference between laminar and turbulent flow. and then we will finish for today. Moves randomly with swirling and mixing, right? So for example is laminar flow, right? Whereas if you go and look at Caroni River when it has flood, right? When there's flood in the river, you see the water particles swirling and there's some tiny whirlpools forming and disappearing and so on. So that is an example of turbulent flow. Right. We can end for today. So tomorrow, let me tell you all what we will be doing, so you all could practice. Read up the notes, right? So we will be doing fluid dynamics, so fluid mechanics, sorry. So learn about pressure, the variation of pressure with depth, what the definition of pressure itself. We'll also be doing kinetic and potential energy, So you could read up the notes on work, energy, and power. And we will start thermodynamics, but I don't think we would be able to finish that. So you could read up thermal expansion and heat and heat transfer. Well, basically read up on the rest of the course was to finish those questions, right?
So there are a few questions in the chat.
Yeah, I'll check in them now. So the structure of this exam is similar to the previous exam, right? So there would still be 5 questions, each worth 20 marks, so it would be 100 marks total. Right. I haven't finished marking all of the courseworks yet, but I'll try my best to send it before the first the exam, right? The 0503. I'll try my best to get it done by next week. Right. Yes, that's all the questions I've seen. Any more questions? Okay, if there are no more questions.
Excuse me, sir. Is it possible I can speak to you after class?
Who is this?
Nicolene Monk.
Oh, yeah. No problem. Alright, so you could pay attention to basically what we did today so far is what to pay attention to. If you could do what we did today, you will be able to do well in the exam, at least up till the parts we did. Like, we didn't cover forces and we didn't cover energy and thermodynamics and so on. So I didn't go through every single thing. So I left out some parts. So so yeah, wherever I left out, and I wouldn't say not to learn it, but pay more attention to what we did today and what we'll be doing for the other remedial sessions too, right? Not just this one, but all of the remedial sessions, including identifying graphs. Yeah, so drawing the forces on the inclined slope, you should be able to do that, right? Identifying the graphs, yes, that is something you should know, right? But I would specifically stress the one with drawing the forces on the inclined slope. You should be able to draw those forces and calculate the components parallel to the plane and perpendicular to the plane. The notes I'm using, I'm not using any notes other than what we covered for the semester. So I just using tutorials and notes. So there's nothing new I really could send you. We should have all the tutorials and notes already. When marking, like for example, a calculation question, the first thing is the formula, right? You always need to have the formula. Then afterwards, correct substitution. So you need to make sure you put in, like, say for example, in the Hooke's law question, you need to make sure you put in the value of k, you need to put in the value of x, the extension, and well, you, to get the correct answer, you need to make sure it's the correct units, right? And then, well, once you do the calculation, you get the correct answer. So for calculations, it's really just those three things: the formula, correct substitution with correct units, and the correct answer. The answer always has to have units, right? The correct units as well. So if you have the wrong unit, you wouldn't get the mark for the answer. If you have no unit, you would not get the mark for the answer, right? So units is very important. That's for the calculation questions. For the theoretical questions, well, that varies depending on the question, but you always need to have keywords depending on what you are talking about, right? Like for example, today, what did we talk about? Like for example, distinguish between accuracy and precision. So you can't just say close to each other and close to a specific value. You need to like state that for accuracy they are close to the true value or the accepted value. So that keyword true value or accepted value, that is something that is key to the definition of accuracy. For precision, the repeated measurements are close to each other. So each other in that case is a key word for the definition of precision. So for each definition, there are some key points that you need to have, right? Like in laminar flow, we talked about, right? Laminar flow is the fluid moves in straight and parallel layers, right? So that straight and parallel layers are the key words for the definition of laminar flow. So when you're writing your answers for the theoretical parts, you need to have those key points. When you're given examples, the examples need to be relevant too, right? Yeah. The document I was writing on, I wasn't really planning to share this document I'm writing on because it just is a set of looking at it by itself, you wouldn't really be able to follow. I do have, they asked me to make a recording of this session, so I do have a recording of the session. I would send it to you, so while I'm talking you could see what I am talking about. But this document itself is just, if you look at it like now, it just look like a set of random formulas, and because it doesn't really have the questions itself, maybe one or two questions, and I didn't even write all the equations. So like all of these, this O to P with an arrow, it wouldn't be too legible to follow by itself. But I will send the link to the recording for today, so if you all want to watch it back, you could watch it back. Right, any more questions? Okay, if there are no more questions, we can end for today. I'm gonna send the link one time for the recording, right? And once I send the link, we will end for today.